Okay, so we're going to use Excel to run various statistical tests here, and specifically taking a look at how to use it for scatterplots, how to use it for simple linear regression, and using Excel for multiple regression. Now, before we get started, you'll want to make sure that if you click on Data in the tab above, that you have the Data Analysis tab available to you. If not, that can be installed as an add-on pack, but you want to make sure you have that before we move forward. So each tab below has data and it's accompanied by several questions. So let's look at this first one. Suppose the Regional Transit Authority for a major metropolitan area wants to determine whether there is any relationship between the age of a bus and the annual maintenance cost. And a sample of 10 buses resulted in this data. So the first question is, what is the X variable and what is the Y variable? Well, the X variable, recall, is the independent variable, and that's the variable that's doing the explaining, sometimes called the explanatory variable. The Y variable, or the dependent variable, is the variable being explained. So in this case, it's pretty clear that our age is explaining a bus's annual maintenance cost. And presumably, we might imagine that as age goes up, the cost is going to go up as well, and that's the question we'll explore here in a moment. Next, it says create a scatter plot to represent the relationship between age and cost. Now, let me give you a quick tip as it relates to Excel to do this that will save you a lot of time. When you're doing this, one very simple way to do it would be to make sure that your X variable is always to the left of your Y variable. The independent variable on the left, the dependent variable on the right, and if you set it up that way, then it's very simple to actually go straight into a scatter plot. So let me show you what I mean. We're going to highlight these, go to Insert, we'll go to Scatter, and we'll just drop down right here, and bam, right away we've got our scatter plot, and we see that on the X-axis we have age, and on the Y-axis we have the annual maintenance cost. And here I'm asked to include the regression equation and the R-squared and interpret. So what you'll want to do here is click here and then click on Layout, and we'll go to Trend Line. I'm going to go to More Trend Line Options, and if we say Display Equation on Chart and Display R-squared on Chart and hit our key there, it'll come right up. Now, one thing I want to point out, when it displays the regression equation, which again, you can manipulate the size and whatnot if you'd like to do that. Notice that this is in y equals mx plus b form. This is not y equals b sub 0 plus b1 x form, or linear form. So what we see here is this is actually our y-intercept, and then we have our slope coefficient for our x value. So in this case, for each 1 unit increase in x, which is a year, we see about $131, $132 increase in the annual maintenance cost. Moreover, our R-squared is 87%, so 87% of the variation in cost is explained by the variation in age. Okay, let's go to another tab here. As part of a study on transportation safety, the U.S. Department of Transportation collected data on the number of fatal accidents per 1,000 licenses and the percentage of licensed drivers under the age of 21 in a sample of 42 cities. Data was collected over a 1-year period. So again, the explanatory variable, presumably, if we just sit here and think about it, is going to be the percent under 21. And the dependent variable, the Y variable, is fatal accidents. So what we're really getting at is, as the proportion of an area's drivers are more or less under 21, does that actually increase fatal accidents? The more young drivers, the more accidents. Is that what we're looking at? So it says to create a scatter plot to represent the relationship between these two variables. And again, notice I've got my X variable on the left, my Y variable on the right, and that's just going to make this very simple for me when I set up my scatter plot. So let's go ahead and do that. Okay. I'm going to drag this over here. I'm going to make this a little bit bigger. Now, one of the things with Excel you'll find when you're doing graphs and charts, tables, sometimes you have to do a little bit of manipulation to make it look a little nicer and more presentable. Here it says write in a title for the x-axis, y-axis, and the chart. All right. So if we go to our design, we've got axis titles, and here we have primary horizontal axis title. Okay, and so as we had mentioned before, this is going to be % under 21. All right, and then our vertical axis, put this here, fatal accidents per 1,000. Again, you can manipulate this as you see necessary. And then finally, we can write in a title, and there all we have to do is click on that, and we can write in % under 21 as it relates to fatal accidents. All right, that might be a bit of a lame title, but and actually I'm going to delete this, and so we see that that gives me a little more space. Now notice it says to rescale the x-axis. What does this mean? Well, if we notice here, from 0 to 8, this is all blank space. And so if we wanted to make this look a little bit different, we can actually double click here, and let's go ahead and start our x-axis at a value of 7. And if we hit close, notice then that this rescales it. 7 is now our starting point, and now we're taking up more space. There isn't as much blank or empty space. Finally, include the regression equation and the r-squared and interpret. I'm going to do one other thing here too. I'm actually going to add a line of best fit. This looks to be a linear relationship, meaning that the relationship between the variables is best characterized by a straight line. So I'll put this in and then click on displaying the equation and the r-squared, and I'm going to drag these out where they are more visible. So again, we see that our y-intercept is negative, in negative territory, which makes sense if we follow this line. And for each 1 unit increase in x, the % under 21, we see a 0.2871 unit increase in fatal accidents per 1,000. R-squared is over 70%. 70% of the variation in fatal accidents is explained by the % under 21. Now let's look at a simple linear regression example. The marketing manager of a firm is convinced that the key to the company's variation in sales relates to advertising. And not just relates to advertising, but directly relates to advertising. So they collect the following data to prove their point, to make their case. So let's create an estimated regression equation to help answer these questions. So advertising dollars, that's going to be our x variable, and how does that explain our y variable, sales? Now here's where we want to utilize our data tab, data analysis, and we're going to just scroll down to regression and click OK. So it's going to ask us to input our y range, which we determined was sales. All right, and input our x range, which we determined was advertising dollars. And notice that I am including the title when I pull this in, and that's because if you click on labels, you're telling Excel that you're including these titles, and I would strongly encourage you to do this because it makes interpreting the output much easier. We're going to leave these blank. We're not going to change our confidence interval. It will automatically input 95%, and we're not going to worry about residuals. We're not going to be doing diagnostics at this point. Output range, I'm going to tell it to put the output right here. I click OK, and there we have our data. Now, one of the things that I tend to do, if you don't input a confidence interval range, it will just repeat a confidence interval of 95%. So this is redundant information. I'm going to get rid of this, And I want to make this a little more readable. Typically, I will draw this down to 2 decimal places. Let me see here. Okay. And again, just making this all a little bit more readable. Now, let's interpret the output that we have. How we want to read this, we first want to look at our r squared. We see that as 0.33. What does that mean? It means that 33% of the variation in sales can be explained by the variation in advertising dollars. Okay? Second, we're not looking at the p-value on the F statistic in simple linear regression because this is basically to tell us whether or not the model is statistically significant. So we're not interested in this when we're doing simple regression with just one independent variable. And then let's go ahead and look at the p-value. The p-value is far less than 0.05. It's actually less than 0.01, which means that we can reject the null hypothesis that there is no relationship, and we can accept the alternative hypothesis that there is a relationship between advertising and sales. And what is the nature of that relationship? Well, we see it here. For each 1 unit increase in advertising dollars, which is $1,000, we get a 0.10 unit increase in sales. Now, is this good news or is this bad news? Well, it's probably bad news. What this means is for each dollar that we're spending on advertising, we're getting back a dime or 10 cents to the dollar for sales. So we would want this ideally to be a value of at least 1.0, that you get out what you put in. But, of course, the larger story is we would want more data. We'd want to control for the other factors that explain sales. Okay, let's look at another simple linear regression example where we do pay attention to our confidence interval. All right, sales manager collected the following data on annual sales and years of experience. Again, this is going to be our X variable, this is our Y variable, and we can presume that what this is meant to mean is that as someone has worked at this company longer, do they actually do more sales? So as they've gained more experience, presumably they're a better salesperson. So we can create a regression equation to explore this more deeply. And let's go ahead and do this. Again, we will click on Data, our Data Analysis, Regression, and our Y variable, our input range will be this. Let's go ahead and click on our X range. Labels is already clicked. And for the output range, I think I'd like to have this come out right here. Okay. So let's go ahead and delete these. And then we're just going to take a moment and clean this up. Make this a little bit more readable. Give a little more space here. All right. I'm going to put this now at 2 decimal places. Okay, great. So, how would you explain this data using a confidence interval of 95%? Well, before we get to the confidence interval, let's just interpret what we know here. Now, we have a coefficient for the y-intercept being 80. And what does this mean? It means that if someone had no experience, we would expect them to do sales around 80. We don't know if that's 80,000 or 80 units or what those units actually mean, but we would expect that to be 80. And for each additional year of experience, for each 1 unit increase in X, we see a 4 unit increase in Y. In other words, sales go up about 4 units or whatever it might be per year of experience. Now, this, of course, is inferential statistics, meaning that we're using a sample to generalize to the larger population. And by the way, both p-values here are less than 0.01, So these are statistically significant values. So we're using this to generalize to a larger population, but we want to be confident. And so we can use a confidence interval. And how we would interpret that is saying we, especially for this value, we're estimating that for each 1 unit increase in sales or in years of experience, this increases sales by 4 units. But we can be 95% confident that the real value is somewhere between 3.11 and 4.89. In other words, there's only a 5% chance that the real value is under 3.11 or over 4.89. And here we say, what might improve this confidence interval? How could we tighten this interval and make it even closer? For example, 3.8 or 4.2. And the answer to that is to increase your sample size. Typically, that's the answer. Why? Because the standard error, this value here, is basically the standard deviation of the sampling distribution. And if you were to look at the actual formula to calculate this, it is the standard deviation divided by the square root of the sample size. So mathematically speaking, the larger your sample size, the lower your standard error is going to be. And a low standard error will tighten this gap, among other things. And last but not least, of course, if we have a good model, we can use this for estimation. All right, so let's do a little bit of this. We've got sleeping bags, we have their rating, and we have their price. So we're looking at the relationship between the rating, the X variable, and the price of that sleeping bag. Okay, so I'm going to go to data, and I'm going to do my regression here. Price is going to be our Y variable, and the X variable is going to be the rating. And let's go ahead and put our output right here. Notice that, again, my labels are clicked here. Okay. And let's make this just a little bit more readable. And those who are more Excel savvy than me probably recognize that there's a quicker way of doing exactly what it is I'm doing right now. All right, so we see that we've got a good model here. 80% of the variation in price is explained by the sleeping bag's rating. That's good. And we see that for each 1 unit increase in the rating, our price goes down by $5.28. Now, that might seem a little puzzling. But notice that we want the rating to go down in order to be better, okay? So we have to kind of wrap our mind around that, like what's actually going on. In other words, if we go from 12 to 13, that's not good. That means the rating is going up, and that's why we would see a negative increase in the price here. All right, so let's go ahead and write out what we know of our regression equation. Y is equal to 359.27 minus 5.28x. And it says, based upon the model, predict what the price would be based upon a rating of 30. All right, so if we put a value of 30 in here, we would just do some simple math. We're taking 30 and we're multiplying that by negative 5.28. And that is a value of 158.40, negative 158.40. And then we want to make sure we add in our y-intercept. And so given this information, we would expect our sleeping bag to be a value of $200.87. I confused Excel when I put my equal sign in there. That was my mistake. All right, so $200.87 if we had a sleeping bag with a rating of 30. And if we want to kind of give this the sniff test, so to speak, let's look at other sleeping bags that are close to 30, all right? We see that this one is 38. We see that this one is 24. and 30 is in between both of those somewhat, and that makes sense. 149, 289. Here we see 25, that's 229. So yeah, I say that because if we had some value of 700 or 1.2 million or something like that, that wouldn't make a lot of sense, and we probably would have done something wrong. This is a very important part of statistics I'll mention to you, and I point this out to students often. When you get an answer, just put your pencil down, put your calculator down, put your mouse down or stylus or whatever you might be using, and just look at that value and ask yourself, does that make sense? Does that fit based upon what I know of the data? And in this case, it does make sense. Okay, so now we're going to look at multiple regression. And if doing the simple linear regression made sense and you didn't have any problems with that, you probably won't have any problems with multiple regression. So let's take a look at this. The Wall Street Journal conducted a study of basketball spending at top colleges. And to the left is a portion of the data that shows the revenue in millions, the percentage of wins, and the coach's salary for 39 of the country's largest basketball programs. So we want to predict the coach's salary, okay, and interpret the coefficients. Now, let me take a moment. I should have said this earlier. Similar to what we did with Scatterplots, you want to make sure in multiple regression that your x variables are contiguous, meaning that they are touching one another. And you'll see why in a moment, and that your y variable is either on the far end of the right side or the left. But you wouldn't want an independent variable, then your y variable, then another independent variable. Here's why. When we go to run the data, we want to make sure that this is our y variable. But when we're doing our x variables, we're going to pull them both in together. So again, they have to be touching, they have to be contiguous. All right? And let's go ahead and put our output right here. And you see that that pulls all of that information in for you. Very simple. Let me clean this up a bit. Okay. So our R squared is about 32%, so a little less than 1/3 of the data is being explained by these variables, a coach's salary. All right. In this case, we do want to take a look at the model. And here we see that the model is statistically significant. The value is far less than 0.05, and in this case, even less than 0.01. So we can say that the model is statistically significant. If we look at the p-values, revenue and wins, both of our independent variables, are statistically significant at the 95% confidence level or the 0.05 level of significance. Here we see revenue has a 0.05 coefficient, and we see a coefficient percentage of wins of 0.01. And how are we to interpret each of those? Well, remember, we have to think here about the units that we have, all right? And the units are in millions. So we have millions here, all right? Obviously, percentage of wins is a little bit different. So for each 1 unit increase in revenue, we see a 0.05 unit increase in a coach's salary. So if revenue were to go up 1 unit, in this case here, $1 million, we would see a coach's salary go up 0.05, and 0.05 of $1 million is $50,000. What about percentage wins? For each 1 unit increase and in the percentage of wins for a coach, we see a 0.01, or again in millions, that would be a $10,000 increase in a coach's salary. So the model is okay, but notice we're leaving a lot of unexplained variation on the table here. So we'd want to throw in more variables, not least of which we might imagine that the coach is pretty good at negotiating their salary. Where do we account for that? Or their reputation at previous institutions, or whatever that might be. But we want to explain more of the variation in salary than what we have here, and we can improve our model by doing that. But the 2 variables we have here are indeed statistically significant. Okay, let's end with doing a couple of multiple regressions that deal with dummy variables. And I'm going to show you how to use an if function in order to write out a dummy variable. So here we have data for water filtration maintenance. And the company wants to predict the repair time necessary for each maintenance request. In other words, repair time is our dependent variable. Further, the repair time is believed to be related to two factors: the number of months since the last maintenance and the type of repair. Are we talking about an electrical repair or a mechanical repair? This latter variable would be considered a binary dummy variable. Binary because it's either electrical or it's mechanical, right? There's not multiple categories. It's either this or that, okay? So we want to write out our regression equation, and that's just simply going to be y, or repair time, is equal to b sub 0 y-intercept plus b1 months since last serviced plus b2 dummy type of repair. Okay? Now, how would I go about doing this? Notice that I say mechanical is 0 and electrical is 1. Now, you could just simply input it, right? This is a 1 and this is a 0, and just go through all of these. We're going to use an if function because if you had, say, instead of 10 data points, 1,000 or 230,000 or whatever and that might be, you can't just simply go through each one. So we're going to use what's called an if function. And what we write out is equals if, and we're saying if A2 is equal to electrical, then we want you to give it a value of 1. But if it's not equal to that, we want you to give it a value of 0. That is our formula. Hit enter, and then we're going to drag this formula all the way down, and bam, that does it for us. Okay? So let's go ahead and run our regression. We've got our independent variable here on the far right, and we have our our dependent variable here on the far right, and our two explanatory variables, our independent variables, together here on the left. So I click on my regression. Repair time is my y variable. This is my x range, my x variables. And let's go ahead. Okay, so here's our data. And let's go ahead and we'll clean this up just a bit. All right. Same thing here, 2 decimal places. You don't have to do 2 decimal places, but it's relatively easy to read. And let's make sure we can read these as well. Okay, what have we got? Well, we've got an R squared of 86%. 86% of the variation in repair time is explained by the month since the last service and the type of repair. The model itself is statistically significant. That's a good thing. Let's look at the p-values. We see that both of these p-values are less than 0.05, so we can say that they are statistically significant. In other words, the effect is real. And now we'll look at our coefficients. So the months since last repair is 0.39. And let's think about the units that we have. This unit would be month, and this is repair time in hours. Okay? So for each 1 unit increase in the months since last service, we see a 0.39 unit increase in the repair time. And so if we're talking about hours, 60 minutes or 1 hour times 0.39 is basically 23 minutes. So we're adding an additional 23 minutes of repair time for each additional month since it was last service. What about the type of repair, the dummy? Well, we see this alone will add 1.26 hours. So for each 1 unit increase, when we go from a 0 to a 1, when we go from a mechanical to an electrical engine repair, we add on 1 hour and not 1 hour and 26 minutes. We need to be careful of that. We could take 60 minutes and times 0.26. So basically we're adding an hour and 15 minutes, a little bit over, by virtue of going from a mechanical engine to an electrical one. All right, so let's do one more of these. This is a 10-year study conducted by the American Heart Association, and it's data on how age, blood pressure, and smoking relate to the risk of strokes. We'll assume the following data are from a portion of the study. And risk, by the way, is interpreted as the probability times 100 that the patient will have a stroke over the next 10-year period. All right, so we want to create a dummy variable for smoker, okay? And we want 0 to be a non-smoker and 1 to be a smoker. Okay, so what I'm going to do is say, if this particular cell is equal to no, then I'm going to put a 0. But if it's not equal to no, I want to put a 1. And we'll hit OK. And if we drag all of these down, we see that we get each value. All right. And so notice that my 3 independent variables are all contiguous, and then my dependent variable is off to the side. All right. So let's go ahead and create our regression equation. And our y variable is going to be risk. And then our age, pressure, and smoky dummy are our x variables. And let's go ahead and put this right underneath. All right, great. Clean this up a bit. Okay, one more. And let's clean these up as well. All right, great. Pretty good model. We see the R squared is 0.87. 87% of the variation in a risk score can be explained by age, the blood pressure, and whether or not the particular person smokes, is a smoker. We see that the model is statistically significant. This is far, far less than 0%. And we see that the p-values are all less than 0.05. Most are less than 0.01. So these are statistically significant at the 0.05 level of significance, or the 95% confidence level. Let's interpret our coefficients. So for each 1 unit increase in age, each year you get older, you're basically adding a point to your risk score, a little bit more. For each 1 unit increase in blood pressure, you're adding a 0.08 unit increase to, a 0.25 unit increase to your score, a quarter of a point. But we see that this is a big one. By going from a non-smoker, a 0, to a smoker, we get an 8.74 increase in the risk score. So just again, by going from a non-smoker to a smoker, we increase that risk score significantly. So our last question says, is smoking a factor in the risk of a stroke? Absolutely it is. And in fact, we can even assess how much it's adding to the risk score of a stroke. All right. Well, we've gone through a lot of material here. There's more we can do, but this is enough information for you to understand how to build a scatterplot, how to run a simple linear regression, and how to run a multiple regression using Excel. Thanks for your attention.